There going to be amines on the poster?
All right, guys, we're going to go ahead and get started. All right, so we have what amounts to really 2 classes left of reactions, and that's sort of where we're going to stop for the next exam. So again, we have an exam coming up effectively a week from today, and that exam is going to cover pretty much all the chemistry that you've learned, starting in Organic 1 all the way up till now. Certainly the emphasis of it will be on the chemistry that we've learned since the last exam, but you are going to be responsible for all the previous material. So, know the current material. That's going to be the most important. Again, Diels-Alder, understand the Diels-Alder transition states, stereochemistry associated with Diels-Alder chemistry and Claisen chemistry. Know the amines, know aromatic chemistry. So there's a lot that I can ask questions on based upon that. So I can imagine filling up the exam fairly nicely with questions from those chapters, but that doesn't necessarily mean that there won't be something, say for example, a synthesis problem that's suddenly going to require you to perhaps pull a reaction from the previous semester. So I'm not going to be going out of my way to ask Organic 1 questions, but this is a cumulative course, and so while the emphasis will be on recent material, you will have to know previous stuff. Yeah. Yeah, I mean, the formats, I don't know. I think there will certainly be synthesis questions. There'll certainly be questions about reactions. I think the important point for you guys is know the reactions, know the mechanisms, know stereochemistry, regiochemistry. Those are probably the most important things, right? Knowing the chemistry, knowing the reactions first and foremost, and then subsequently, and within that, I think understanding the mechanisms. But there are instances now where we have some things like transition states, which you'll need to know. For example, the Cope and the Claisen or Diels-Alder. So that's something that I think you'll almost certainly get a question that's going to deal with some transition state of one of those, because this is my one chance to ask a question like that, maybe on the final as well. But yeah, so I know the transition states of these molecules, understand the diastereoselectivity that comes through those, understand regiochemistry, selectivity. So there's an element of selectivity that we've sort of stepped up to at this point that I think we need to know. So again, don't freak out necessarily and start having to reread all of Organic 1 material, because certainly the bulk of the material will be on stuff like I just talked about, everything since the last exam. And again, I think I could put together a good exam just with that material. But again, I can imagine that in a synthesis problem or something, information from previous could come up. So, so be aware. Okay, so the chemistry that we're going to learn today, and to a certain extent tomorrow, is going to be a little bit different than what we've seen in the past. It involves metal-catalyzed carbon-carbon bond-forming reactions, and specifically, did I say this? Catalyzed. Did I say catalyzed before? So we've looked at metal-based carbon-carbon bond formations in the past. Today we're going to deal a little bit with metal-catalyzed processes, in part because these metal-catalyzed processes have become a pretty big deal. In fact, the 2 classes of reactions we're going to discuss today and tomorrow were both 2 of the more recent Nobel Prizes within synthetic chemistry. So if you think about organometallic chemistry from previous, we've often seen organometallic chemistry as a really good way to sort of gain entry into new carbon-carbon bond-forming scaffolds. And trying to think of the first example that we saw. I don't remember which one was the first, but one that you all know pretty well by this point, right, is the Grignard, which would certainly classify as an organometallic process, right? This is where you would take, say, for example, R1 and a halogen, right? You take that and you treat that with magnesium and make what we would refer to as a Grignard reagent, right? We can think about this as being sort of an anion with perhaps some magnesium bromide counterion, right? And we know that this Grignard is now a really good nucleophile. So You can imagine, again, you might have heard of Ward's coupling, where this will react with itself, which is a problem within Grignards. But really where Grignards are mostly seen is in reactions with carbonyls, right? And so you'll take a compound, we say a ketone, for example, right? If I just show some general ketone there, what's going to happen is, right, the nucleophile is going to add into this carbonyl. Right, and then following an aqueous workup, you'll end up with the alcohol. And again, this is just a generic example, but it could really be any carbonyl. Right, we saw this at the beginning of the semester. It could be an aldehyde. It's actually very reactive with an aldehyde. It can also be with esters, and we've seen in the case of esters, sometimes it'll add in and then add in a second time. Okay, so this is probably one of the first organometallic reactions that we've seen. And the one that's going to be a little bit more analogous to what we're going to see today is the Gilman reaction. In the case of a Grignard reaction, so your nucleophile has this sort of character to it that we'll sometimes call hard, and what that means is that it will behave as a nucleophile, but can also have these cross-reactivities like a base. And so one of the issues that you can often have with the Grignard is that the Grignard will, say for example, you're trying to treat it to an alkyl halide. Sometimes you might get things like elimination chemistry. The Gilman reagent, on the other hand, again, you can start from a similar sort of species like a bromide, but the Gilman reagent is effectively cuprate based, right? So what we're going to do in the case of the Gilman reagent is going to be a two-step process where first we treat it with some type of lithiating reagent. So sometimes you'll treat it with butyllithium, sometimes you can treat it with sort of lithium zero. And then what generally you'll do in the second step is treat this with a salt, sometimes with copper salt, so usually, say for example, copper iodide, right? And what essentially happens in this case is that you get a reagent, right, where you get this sort of Gilman reagent, right, this sort of QLE. And again, there's sort of two equivalents of the alkyl halide that end up in here. Your sort of byproduct in this case is an equivalent, in addition, of lithium bromide. But with this, we've seen that you can begin to actually get to nucleophilic chemistry that you might not be able to previously, right? One of the things in particular, again, the Grignard, while it might be able to react with, say, for example, an alkyl halide and displace that alkyl halide, what a Grignard is certainly not going to react with is an sp2 hybridized electrophile, right? And so where Gilmans have a lot of value is if you treat them to, say, something like a vinyl iodide, right? If you take a Grignard and you try to treat that vinyl iodide, it's not going to react, right? You're not going to be able to do standard substitution chemistry at the vinyl iodide. But one of the things with the Gilman is that, in fact, you can do this chemistry, right? You can take a Gilman, you can treat it with an sp2 hybridized halogen or leaving group triplet or something like that. And once you can get into this case is you can begin to get the situations where you have, again, and just the sort of one that I've shown here, you can sort of make that carbon-carbon bond. So Gilman is one of those sort of last reactions that we learn in Organic 1. And one of the reasons why it's one of the last reactions that we learn in Organic 1 is often because the Gilman reagent is so powerful and such a useful transformation, at least on paper, that undergrads will often just use Gilman over and over and over and over again as their way to make carbon-carbon bonds. And so we try to get you guys thinking about other functional groups as well. And so we introduce Gilman a little bit later. Again, because you can imagine a situation now where you take any R1 and you take any R2, right, and now we can begin to make those carbon-carbon bonds, right? And again, it's this sort of reason, and I remember when I taught the course, I said, you know, you're going to be tempted to just use the Gilman all the time, and if you do that, you're not going to develop the other reactions within your syntheses as well. But again, within that, the whole reason, for the same reasons that it might be easy for you guys to begin to think about making molecules using a Gilman reaction, you can imagine that as synthetic chemists who are trying to make molecules, they would also find this very valuable. But one of the issues in the Gilman reaction is that you're often sacrificing a couple equivalents. You're using sort of stoichiometric amounts of copper, And so again, just look at this part in general. Again, imagine that you have some alkyl bromide and you've spent many, many steps making it, and then suddenly you're having to throw away half of it just to do this coupling reaction. And so as it turns out that there have been discoveries made over the years that can do a very similar type of transformation, but can in fact do it catalytically. And that's really going to be the sort of the heart of our discussion today on palladium-catalyzed coupling reactions. Okay? And to sort of start with this chapter, I just want to talk about one sort of mechanistic, because we're going to be doing mechanisms today that are a little bit unlike what we've seen in the past. We're going to bridge into and get into a little bit of organometallic mechanisms. And unlike previously where I said you're not responsible for these types of mechanisms, again, I'll show you the mechanism now, and maybe what I'll say is you're not going to be responsible for these mechanisms for this upcoming exam, but you will be responsible for them for the final, because these might take some time. So I'm going to show them to you. You're going to be responsible for them on the final. You'll almost certainly get mechanisms on the final, but given the fact that you've got only a week to do it before the next exam, you won't be responsible for these mechanisms for the next exam. But you will be responsible for the reaction that we learned. Okay? So, at the heart of sort of, I'll just say, palladium-catalyzed processes, is this sort of idea that palladium can effectively, again, there's sort of numbers behind this that I don't necessarily want to get into, that you can take an organometallic course and learn about. But there are what we call different oxidation states of transition metals. Okay? And we've perhaps seen them a little bit in the past, but effectively what this means, and I'll just try to sort of simplify it for you, is that sometimes you'll see palladium that will be in this sort of zero state, which is effectively like the metal's way of being neutral. I guess it's not entirely accurate to make that analogy, but at least we can think about it as being the palladium is neutral. We also have palladium-2, okay, and again, some of the chemistry that we're going to see is going to be the change between palladium-0 and palladium-2, and I'll explain this in a moment. But generally, when we'll write this, we'll often use the Roman numeral 2 to sort of describe that oxidation state, and then meanwhile, as you might imagine, palladium-4 as well. And so a lot of the chemistry that we're going to deal with that involves palladium-based catalysis is really going to be dependent upon palladium in these three oxidation states. And without getting too much into sort of ligand and ligand theory and so forth, the important part to sort of think about is that as you move up an oxidation state, what you'll have and what you'll see in these, oftentimes there's a lot of other ligands that you'll see, like triphenylphosphine can be bound, for example, one of the very standard palladium zeros will be palladium, what we call tetrachus. And so I'll just try to explain this very quickly, but it's not going to be necessarily something you're going to be responsible for, but hopefully it'll make sense of these processes moving forward. But palladium tetrachus is a catalyst that's kind of the standard palladium zero species. You'll see that it's got all these phosphines bonded to it, but if you actually think of those phosphines in and of themselves, they are, if you think about triphenylphosphine is neutral, right? And as it turns out, as we begin to move up to other catalysts, and we go to palladium-2, for example, what you're going to have is you're going to begin to have ligands that don't have neutral species to them. So say, for example, palladium acetate. So palladium acetate or palladium-2 acetate, this is a form of palladium-2, right? And what you notice about the ligands in these cases are that the acetates are in fact negatively charged, right? And so you can think about that bond between the palladium and the acetate as almost being a covalent bond. Whereas in this case, it's sort of, maybe we want to call it a dative bond or just a coordinative bond. In this case, we've sort of drawn it, and it's more of a covalent bond. So anytime you see a sort of a ligand that can bear a negative charge on it, that effectively becomes, you can sort of, as you're sort of counting, every time you see a ligand that might be able to bear a negative charge, that's a ligand around it, you'll start to see that have that charge on it. So this might make a little bit more sense as we're moving forward. And then meanwhile, something like palladium-4, I don't know that there's any catalysts that are palladium-4. There's no catalysts that are palladium-4, are there? It's too unstable. Right, but what we'll see a lot of times is, say for example, palladium-2, and we'll get into this in a moment, if we'll see systems where this will make more sense in a moment when I go through the catalytic mechanism. But here's a case where, if you imagine taking the electrons and pushing them here and pushing them here, again, we already discussed the acetates, but there's an R group that has a negative charge, there's an X group that has a negative charge. And so this is an intermediate state that we're going to see from time to time, and this would be what we would call palladium in the sort of 4 state, again, because it has 4 effectively covalent bonds, if you will, sort of around it. Okay, and when I'm saying that, it's perhaps not the best sort of way to characterize it as a covalent bond, but a better way to think is if you sort of move the electrons, right? Palladium, triphenylphosphine. If you move those electrons onto the triphenylphosphine, right, the triphenylphosphine is neutral, right? If you do the same thing with, say, an alkyl group, or you do the same thing with an X group, right, there's going to be that negative charge. And so what we'll see is when those groups are around it, if you can sort of push the electrons from that metal onto that ligand, if suddenly there's a negative charge, then that's going to be what we call a sort of a -1 ligand. Whereas if you sort of push those electrons onto that group and there's not a change, then you don't see that. Okay, so we're going to see some of these different oxidation states within the sort of palladium catalyzed process. Now, why this is important is that by transitioning through a lot of these different oxidation states, we'll start to see that a lot of interesting chemistry can begin to take place that effectively involves the shuffling between these different oxidation states. And the sort of standard one that we have, and we'll give it a sort of a name, okay, is a sort of process whereby if you have, say, palladium-2, sometimes you'll see it draw like this as well. So this equals, so sometimes you see the palladium in brackets as a 2, sometimes you see the palladium sort of superscript 2. I apologize if I will sometimes switch between the two. I'll try to stay consistent with this just because it's neater, but I may be switching back and forth without really needing to. But what happens in sort of palladium chemistry, and we'll see this, I'll show it with palladium-2 and then I'll show it with palladium-1, right, is that if you have a ligand that's, or a palladium source is palladium-2, regardless of what it is, what can happen is you can begin to insert into electrophiles, okay, into the electrophilic bond. So as I sort of shown there, an alkyl bromide, okay? And the net result of this, okay, is that this is sort of analogous in many ways to how the Grignard, right, how the magnesium of the Grignard inserted, right, into the carbon-bromine bond. So it's very analogous to the magnesium, right? The magnesium inserted in between the two bonds. In this case, it's going to be the palladium that's going to insert into these two. And so this process that we have going from here to here is what we call an oxidative insertion. Because as we start with palladium-2, what we're going to have over here is palladium-4, right? And if you think about what the term oxidation means, right? Remember the oil rig, oxidation is loss. So in this case, what's happening is it's an oxidative insertion because the palladium is becoming oxidized through the process. It's losing 2 of the electrons to become a palladium-4 species, right? Likewise, the reverse process, right, where you would suddenly lose RBr, right? That's not oxidative, then it's what? Reductive, right? And so the reverse process is called what we call reductive elimination. And again, that elimination term can be very analogous to, say, for example, you know, if you think about the fact that when we talk about elimination chemistry, we were sort of often losing HX in some way, right? A proton was being extracted, we were losing some type of hydrogen. And so again, you have this sort of reductive elimination process there. And so, again, I've shown it as palladium-2 to palladium-4, but certainly you'll see oftentimes the same thing between palladium-0 and palladium-2. So sometimes you can sort of shuffle between palladium-0 and palladium-2 as well. Okay? And so as we start to go through a lot of the chemistry today, what we're going to sort of see is these processes of, I'll just say OI, RE, these processes of oxidative insertion followed by reductive elimination. Okay? So these are going to be at the heart of pretty much all the palladium-catalyzed chemistry that we're going to discuss today. There will be some differences that separate several of the reactions that we're going to sort of learn. But what we'll see is that this overall oxidative insertion, reductive elimination, transitioning between a lower electron, a higher metal with more electrons going sort of a lower electron, so again, palladium-2 to palladium-4 or vice versa, or in this case with 0-2. And so this sort of back and forth between these two processes is going to sort of rear its head in a lot of the chemistry we learned today. And so the way that the book moves forward in terms of discussing this, it starts with a reaction known as a Heck reaction. I'm actually going to introduce that towards the end because I think the sort of, at least in terms of knowing reactions, the Heck reaction is a little bit different than perhaps what we've seen before. But there are a series of reactions that are very analogous, I think, to what we've seen in the past, specifically with the Gilman. Okay? And so it turns out that one of the things that you can do that's fairly common, there's many reactions that have this, right? That if you take some type of metal, alkyl metal, and we'll get into what those metals can be in a moment, and we treat them with an alkyl halide, right? And we then take this compound and treat it with a palladium catalyst, so in this case I'll just say palladium-0, okay? What can happen is, it's catalytic, so you keep regenerating at palladium-0, but what's going to happen is you're going to end up making that carbon-carbon bond. And so if you treat the metal and the bromide together, depending upon the metal, sometimes these might react with one another, but the palladium will accelerate that process. Oftentimes the metals that are chosen will not react with one another by themselves. You'll need that palladium in order to happen. And so the mechanism of how this is involved, this is what we call sort of palladium-catalyzed cross-coupling reactions. And again, the mechanism starts right back where we sort of discussed earlier. Okay, so if you start with, and we'll draw this in sort of a circle. Okay, so we'll see these sort of catalytic cycles, right? These sort of circles that will sort of go back to the sort of product. And so what will happen in this mechanism, as you might imagine, as I sort of just pointed out, is that sort of oxidative insertion. That's going to be the first step. In the case of palladium-0, what's going to happen is that's going to go to palladium-2. Okay? And what's interesting about the metals in these cases is there's a process that can take place that's actually called a transmetallation, where if you have one metal, and in this case in this sort of higher energy oxidation state, what can happen is now that second metal can come in, that R prime metal can come in, and effectively what happens is it almost exists as a nucleophile on the palladium species. Okay? So what's going to happen is your R1, as I've shown here, is now actually going to displace that metal bromide bond. And what you get is this sort of transmetallation. Yeah. Okay? So what's happening here is that the metal carbon bond does what we call a transmetallation. Again, you can formally think about it as perhaps nucleophilic attack on the palladium and leaving that metal. You can think about it as a sigmatropic rearrangement where the metal bonds here and the R group kicks over in terms of the, that'll be similar to, maybe the 2 electron push that you see in the Wittig reaction. But it's not clear, to me at least, exactly what that mechanism is, but it's an overall process called a transmetallation. Okay, and so the net result is an alkyl halide that's known. You'll generate this new palladium species, right? And then what's going to happen in this case is we're going to do a reductive elimination. Okay, and during that process, when we do the reductive elimination, now we're going to regenerate palladium 0, right? So here's palladium 0, but we're going to sort of regenerate that initial oxidation state. Yeah. This? The reductive elimination. Reductive, it gains electrons. It goes from 2 to 0. So now it would react with the second equivalent of alkyl halide, making palladium 2. So it's basically 3 steps. Oxidative insertion, reductive elimination, and those are going to be the 2 steps behind everything. But in these cross-coupling cases, there's one additional step in there, which is at this phase, you do a transmetallation. So it's the same thing. You're just, whether it's 2 or 4, you're just switching between 2 and 4 if your catalyst starts at 2 and that's reactive enough. Or what can happen is you can switch back and forth between 0 and 2. And so in general, when I've run this reaction in the past, I've had better luck at starting with palladium 0 catalysts. And oftentimes, when you have a palladium 2 catalyst, it oftentimes has to be reduced first to a palladium 0 catalyst. Because palladium 2 catalysts are more stable. That's sort of the natural way that they want to be. Like, there's palladium tetrachus, for example, is a very common palladium 0 source, and we store it in a glove box, right? So, like, when the students want to actually work with it, they'll pump in their stuff. They'll go in with these big gloves and they'll weigh it out in there, because what will happen is if you expose the palladium 0 to oxygen in the air, it'll actually decompose and go to a palladium 2 species. So oftentimes you'll have a palladium 2 species and you'll have something in there that will bring it to the 0 and then back to 2. But again, the important point for you guys, that's more sort of in detail, the important point is that you're sort of shifting between 0 and 2. But that would be one catalytic cycle. But again, if you started instead with a palladium 2, then everything else would change. Right? It would go palladium 2, palladium 4, back to palladium 2. And so these are the sort of possibilities that can sort of take place. And different metals, there's different metals that can do this. Nickel is often fairly common at doing cross-coupling reactions. People have been getting into iron because it's cheaper as a way to perhaps get into cross-coupling reactions. But palladium is really the sort of standard, and it's the one that was one of the early ones to work really well. It's the sort of general go-to cross-coupling method. Okay? All right, so if this is your sort of standard catalytic cycle, okay, so again, if that helps you remember it for now, great. I won't have this on the exam, but it might be it will be on, something like this will be on the final exam. So there will be a mechanism question like this on the final. Okay, so within this, there's a series of reactions that all have different names. And really all the different names depend upon what the sort of source of metal, quote-unquote, metal is. And your book has a list of different ones which you can sort of read about. I'll sort of discuss the sort of standards that we work with. And then I'll talk about what are the situations where you can actually do the cross-couplings. And what I'll do is I'll use that to transition to hex coupling because there's something kind of important there. Okay, so the sort of standard, it looks like the book only taught you 2. So I'll just show you the 2 standards. So the 2 most common, I'll show you some of the others, but the book only really discusses 2. So sort of Stille cross-couplings. Stille cross-couplings are where your metals are tins. So So metal equals SR3. So again, you have some group over there. This can actually be a little bit complicated, and actually we were just dealing with this a little bit in our lab, where oftentimes the tin will have other alkyl groups on there, and sometimes those other alkyl groups can serve as the sort of alkyl source, but there's apparently ways around it. But a very common one will be tetrabutyl tin. So tetrabutyl tin is perhaps one of the most common ones to sort of use. And so, say for example, if you want to make a tin species, so there's a bunch of these that are commercially available. These have been widely used, for example, in medchem studies, because a lot of times people like to employ late-stage cross-coupling reactions to do this. But the way that you would generally make a tin is take your sort of say, for example, a Grignard, right? So you can get to the Grignard or even the alkyl lithiums. You'll effectively take them, and there are things like tributyl tin. The tributyl tin chloride, that's a common reagent, and effectively what will happen is you can make your tributyl tin compound. Now, what's important here is that while each of these butyls, and I'll get to this in a little bit, but the sort of transfer from the carbon-tin bond, again, you see there's actually 4 carbon-tin bonds around here. There's a preference to go, the carbon that's going to migrate is more likely going to be the sort of one that's sp2 hybridized. sp3 is much more sluggish, and it also has some other potential issues involved, but generally it's this one that's going to transfer, and you don't have any issues with this. And so again, this is how you would make these. This is called the Stille. Now the Stille is perhaps the go-to cross-coupling method. It's the one that generally works the best. Well, it doesn't necessarily work the best, but tin is fairly mild in terms of reactivity. There's not going to be a lot of cross-reactivity necessarily with alkyl tin species, and so you can get a lot of sort of what we call orthogonality, right? You can just do that chemistry, and the tin won't go and start doing other things. There are cross-coupling reactions. It's the Kumada Grignard? So right, so if you have an alkyl Grignard, right, that's a cross-coupling called the Kumada coupling. But again, you can imagine that the Grignard might start doing other things. And so while a Kumada might be a better nucleophile to use, it may lead to other products. So generally the tributyl tin species are the ones that are often used the most. Now the problem with tin is it's kind of nasty. It's a pretty bad carcinogen. So while it's stable and has all those favorable properties, it's fairly toxic. Mark Bisco at City College will argue that it's actually not that toxic. It's just certain species of it that are toxic, like the alkyl tin species. It's often said to lead to hair loss, which is what I say is the reason I lost my hair. So a lot of times if people can avoid using tin, they like to. And so while tin often works the best, the one that is sort of preferred, you do it if you can do it, is called a Suzuki. And the Suzuki cross-coupling, in the case of the Suzuki, the metal is sort of boranes. Okay, so I'll just say Br2. And as we'll see, generally maybe I'll even take a step back from there and I'll say the boronic acid. It's a little bit more complicated than this, but you sort of go to this boronic acid. But there are other, you can do some of these other ones as well, but really they often go through, a lot of times the mechanism involves going through the boronic acid step. Now, the Suzuki is really useful. Like, again, people rather use boron than tin because of the problems I just outlined, using it in a stoichiometric amount. But one of the challenging things about Suzukis is that what you actually have to do when you're doing a Suzuki coupling is the transmetallation can't take place at this neutral borane. So oftentimes these reactions are run like sodium hydroxide or something like that. And the reason is that the more active species is the borate. right? And so oftentimes what you'll need is like water or methanol, and it's going to be a basic form of these. And so a lot of the problems that you might see if you've got, say, an ester in there that might hydrolyze under acidic conditions, we were having issues with it because we were getting oxymycyl addition where we had a compound, we were getting 1,4 addition of the hydroxides. Again, we tried avoiding the tin at all costs, but at the end of the day we had to come back to the tin. So these are really the two go-tos. This is good if you can do it, again, because of those toxicity concerns, and it works great, but it does involve things such as hydrolysis. Now, in the case of Suzuki's, you guys have sort of seen how to make boranes in the past. For example, right, if you have an alkyne, right, we learned you can effectively take these and treat them with sort of borohydrides. So what was the one that you guys, it's like the SIA, I don't even remember what it is. But like you do this sort of hydroboration across it, right? If you guys remember this a little bit. So this is one way that you can imagine getting access to these borons. I'll just say sort of R2. So you can certainly do hydroboration against that, but there's also an analogous process to here. And when I made a borane reagent in the past, what I had done was I actually made an alkyl lithium species, and then I treated it with trimethoxyborane. Or actually, it was something slightly different than that. But again, you can sort of see parallels here. There are things like this trimethoxyborane. So it's three OMEs, and if you treat your alkyl halide with it, what will happen is you'll get to, right, you'll get like methanol, okay? And then again, you can hydrolyze that off with various conditions. So again, the sort of synthesis of tins and borons are perhaps a little fairly analogous to what we've seen in the past. You can either take a nucleophile and treat it to the resultant tributyltin chloride. They also have boron chloride, so like you can have alkyl borochlorides that will work as well. But again, you can also imagine using your sort of hydroboration style chemistry as well, where you can effectively add the borohydride across that alkyne. Yes? How does it go from the acetate to the reductive elimination state? How does the metal leave? It leaves as the butyl hydride. It leaves, if you look at the mechanism I had up there previously, it leaves, let's erase this, but it leaves, so in this case, it's effectively, remember that every reaction that you've seen is reversible, right? And so the oxidative insertion, the reverse of that would be the reductive elimination. So you can go back in the other way via reductive elimination. Effectively what happens is the same as an insertion, but just the reverse of that. So again, how you would draw the electrons, you can imagine, I'm not exactly sure, but you can imagine them coming close together and just drawing a mechanism where you might have, where they start to come closer. And again, I'm not entirely sure if this is how it would work, but it would be, you can imagine it being something like that. So it would just be the reverse of the oxidative insertion. So again, that's not really something that we, for example, for the Grignard, we didn't really discuss how we inserted the magnesium into the carbon halogen bond. It just, you sort of knew that you take an alkyl halide, you treat it with this metal, it does this insertion. So in this case, it's important that you don't necessarily have to draw mechanism arrows, just show oxidative insertion, reductive elimination, and that's going to be fine within the transition metal stuff. Okay. Okay. So again, these are the two big guys, and in fact, Stille and Suzuki, in addition to another person that we're going to discuss in a little bit, Heck, really made the contribution. Well, made among many others. They were actually awarded the Nobel Prize for cross-coupling. And we'll talk about hex in a little bit, but you can see these sort of extremely well known names, or sorry, these extremely well used reactions. People that are associated with the names have actually won Nobel Prizes because of them. Okay, so what can you do? The next question is sort of, when can you do cross-couplings and when can you not do cross-couplings? And again, we can sort of very simply say R1 and R2 can come together, but as it turns out, that's not necessarily the case. And that's probably good that that's not the case, because a lot of things like tributyl tin, the fact that certain tin alkyl bonds go slower than other tin alkyl bonds allows some of this chemistry to actually be usable. So if you're going to do a cross-coupling, okay, if you're going to begin to do sort of cross-couplings between these two, we have to start thinking about the issues that are involved with them. And so when you have an R group, the sort of ones that work really good are sort of aryl, sort of like aryl metals or alkynyl metals. Okay? And as it turns out, you can also do alkyl, so you can actually have sp3, so sp2, sp2. But in the case of sp3, you can, but it's a little bit more slow. Okay, and so it turns out that in the case of sp3, we won't go into too much detail behind it, but there are sort of things that you can do to have metals. There are specific metals that have been developed that will allow for sort of cross-coupling to take place. Now, you can imagine that in the case of the tin, that might be a little bit tricky, right? Because oftentimes the reagent is tributyl tin, and so now you're competing you got 3 butyls for every 1 alkyl, so there is that crosstalk, but certainly developments have been made for tin reagents that can actually do this. And again, I sort of brought up Mark Bisco's name in the past. He's up at City College, sort of a colleague of mine, and he in fact works with a type of tin that actually allows him to do a lot of this sort of cross-coupling in this way. Yeah, Felix. That you can do carbon-carbon cross-couplings that were completely... So there's 2 really important factors. The one is carbon-carbon bonds are the framework behind anything, behind almost every organic molecule that you can imagine, right? So there's that one aspect to it. Why is it an absolute huge deal? It's that what people have been able to do is use this to huge advantages for medicinal chemistry-based pursuits, right? And so if you have, say, for example, a pharmacophore, say, for example, an indole, this is an example. Say that you've got this indole, and you know that the indole is really helpful for drug development. Now imagine that you're in a pharmaceutical company, and you can say, for example, put a bromide deposition, and you know that there's alkyl groups out in this region that work. Now you can have all these other, or even transmetallate this to a tin, and then take all these other alkyl halides and just make analog after analog after analog after analog after analog, and those can be tested to try to optimize for new drugs. So it's really made, specifically in medicinal chemistry, it's been huge, just because of the fact that you can, you can get to much more diverse libraries fairly quickly. But yeah, I mean, carbon-carbon bonds are the essence behind everything, yeah. Yeah, you might be wasting a lot of things at that point, and it's not necessarily going to be as clean. And so what you see is, if you go to like Sigma Aldrich is one of the chemical catalogs. If you go to Sigma Aldrich, they'll have you can buy libraries of different aryl tins, right? And you won't get much of it. You might get like a milligram of each one. But the idea would be is that you could take those and then they just do all these different cross couplings, and they'll actually do it in parallel, and all, so it's really just opened up. It's had its biggest impact probably in medchem, but we use it a lot as well. I mean, we're, for example, Danielle's work, we're using aryl halides and cross couplings to be able to gain access to molecules that are important for us in that respect. And Mike is also, who's another grad student in my group, he was interested in one series of molecules, and he was developing a lot of chemistry. So everybody's using it, in part because it is that valuable. Okay? Now, on the alkyl halide, I'll use this as a sort of a means into the Heck reaction. Alkyl halides, people are getting better at a lot of this stuff, but it's very difficult. In general, you want to sort of, for practical purposes, you often want to just focus on sp2 cross couplings, but certainly you can do sp3 cross couplings as well if your metal is sp3. In the case of the halogens, and you can do alkynes as well. Halogen, right, because we can have iodized chloride. So again, you can do sp, sp2 works really well, but in the case of halogens, it's very difficult to do sp3 cross couplings, and I'll explain the reason in a second. So historically, people have come up with ways around this, but in general, you want to avoid sp3 cross coupling. And again, there's a guy named Greg Fu, who's out of Caltech now, and he's developed some nice catalysts that can sort of help and allow for these cross couplings, so you can actually do sp3. But that's a really recent development, and it's really challenging to do. And the reason has to do with a potential side product within the overall process, and I'll use this to sort of transition into Heck chemistry. So, this is a process that we call beta hydride. Elimination. And this will be actually valuable for Heck chemistry, but for cross-coupling chemistry, it's actually not that helpful. It actually has the opposite effect. And so if we think back to our catalytic cycle, right, if you have palladium 0, and we come in with an alkyl halogen, okay, of some type, okay, what will happen is you'll do that insertion, okay, so you'll do that insertion, but there's one problem here, and that's that when you're at a species like this, something else happens much quicker, and it doesn't necessarily allow for the transmetallation. So if you want to do the transmetallation, so what you would want is then your metal to come in, right, and get to your palladium, metal R2. What you'd want to be able to do is get to this. And again, people have developed stuff such that you can do this chemistry, certain ligands and so forth. But what's historically been a big problem here is that when you try to do this chemistry, you don't get this. And the reason is that a side reaction takes place. And it involves, again, sort of a beta hydride. Okay, and so the beta, we're talking about to the palladium, 1, 2, so alpha, beta. We're talking about that hydrogen right there. And what happens in this process is that instead of doing the standard transmetallation, what will trump that, what will happen faster than that, is this process called beta hydride abstraction. So what will happen is you will get an alkene, okay, as well as the palladium hydride source. Right? And then again, you can imagine that undergoing reductive elimination to generate HCl or something like that. But again, this is not going to be productive, and then suddenly the reverse of this becomes very sort of difficult often. So again, this is the reason why in general you want to avoid sp3 bonds, is this sort of reductive elimination. Or sorry, this beta hydride elimination. Now, the first metal catalyzed cross-coupling that was actually ever discovered, in fact, involved this sort of process, but in a sort of beneficial way. And this will sort of transition into that reaction. And this is the third of the Nobel Prize winners, has named after him. And so this reaction actually predated that's why the book discusses this one first, but I wanted to show this first. So the Heck reaction actually is the first palladium-catalyzed process. And the Heck reaction, again, is going to sort of leverage carbon-carbon bond forming processes. But what it's going to do is it's in fact going to take alkenes, okay, and it's going to allow us to begin to do chemistry with it. And so what we'll see is we might be able to imagine some further products that might form down here in addition to the other processes that we mentioned. And what happens in a Heck reaction is that if you have, instead of a metal, instead of an alkyl metal, if you have an alkene, and you have an alkyl halide of some type, so we'll just say, make this R1, and we'll make this R2, and you mix these together in the presence of a palladium catalyst, what's going to happen is you will actually make this new bond here. So you effectively swap out a carbon-hydrogen for a carbon-carbon bond. Okay. Now this is a process that is a little bit different, but involves a lot of the sort of same chemistry. So it's not going to involve necessarily the reductive oxidative insertion, reductive elimination, but it's very similar. And what it's going to sort of, well, I take that back. I mean, it will involve that, but not towards the end step in terms of the bond forming. So what happens in this case is that if you have, say, palladium 0, and you treat it with this compound, again, it's going to be analogous to what we saw before. We're going to get this oxidative insertion. Okay? But now instead of the metal, what we're going to have is the alkene. And what can happen is that the metal carbon bond can actually add across the alkene. So if we take this and we treat it with an alkene, what will happen is we'll actually add across that bond. Okay? Sort of the way that I've shown here. Now there's certain regiochemistry to this. You can perhaps explain this regiochemistry based upon sterics, right? Because the R2 is likely going to be much bigger than the bromide. So again, the alkyl group over here will be away from that. What will happen is now you'll have palladium there. And I'll just rotate around to put the group down there. But again, what you also have here is the same thing that you have here now, is you have that beta hydride. And so what's going to happen is, again, I'm not really showing stereochemistry here, but you're going to get that beta hydride elimination as well. Okay? Okay? And in this process, generally what you'll have in this reaction is actually a base. So when you run this reaction, oftentimes what you'll have is triethylamine. And you can think about the triethylamine in a couple different ways. Again, you're sort of generating HBr or HCl or HX, whatever we have here, you're going to generate that. And so on one hand, you might think that the base is there to sort of sequester that acid so it doesn't go and start doing bad things. But in fact, it also helps facilitate this. So you can imagine a mechanism where the base will actually facilitate the leaving at this step as well. So again, it effectively helps. It's probably best to just think about it as sequestering that HBr. But again, you notice that this is very analogous, right? We see an oxidative insertion, okay? But in this case now we're going to add across this bond. So it's, I forget what the exact name of this is, but it's effectively an addition across the alkene, say alkene addition. And then again, the same thing, this is for the same reason why you don't want to use sp3 halogens and cross couplings, this beta hydride elimination takes place. This is what I meant earlier. The beta hydride elimination is what's going to lend to the product. There is effectively a reductive elimination, but you can sort of think about it as the next step. So the product formation is taking place via the beta hydride elimination. Yeah?
Well, we talked before about not using the alpha halide Fe3.
Right.
If we're using that or halide, we're not running.
Yeah, so that's right. So certainly alkyl halides are a little bit more sluggish, but yeah, so if you wanted to use, say, trimethyl-tin or tetramethyl-tin as your reagent, for example, yeah, you would get the metal, no problem. So it's more about them having that beta hydrogen. So along those same lines, you could probably imagine others that wouldn't have that same problem, like benzyl bromide, right, wouldn't have that problem. So that's a great point to make. It might not necessarily want to be generalized for sp3. It's just more of recognizing whether or not that sp3 halogen happens to have a beta hydride that could be extracted. So thank you, that's a good point. Okay, so this is the Heck reaction. Again, we'll sort of see parallels here, but for the point of this exam, I'd expect you to be able to sort of, looking at the conditions, be able to predict this and perhaps use it in a synthesis. Now, we haven't really discussed in depth this mechanism, but just remember that every step is reversible, and oftentimes when global systems are reversible, what product do you generally get? The more stable product, right? And so, as you see, I sort of drew it as the trans, and that's likely the result of the fact that, you know, the lower energy system for the beta hydride abstraction is the one that's going to be there, and that's likely going to be the one where the alkyl groups are away from one another. Okay, so that is the Heck reaction. And in the last 15 minutes that we have, I will show one additional reaction. Actually, we've got two, yeah. Well, yeah, maybe not, yeah. I mean, it's catalytic. It's intermediate, it's not the final product, right? When the reaction's all said and done, yeah, you'll probably be hanging out at the palladium too, right? And sometimes that will actually be the indicator, like you'll be running a reaction and you'll know the reaction's done because the reaction will turn from like a canary yellow to like just black. And that can often be an indicator that the reaction's done. Because now you're at palladium 2 and you're stuck at palladium 2, whereas throughout the various other processes, there's a little bit of palladium 0 being generated to facilitate the overall process. So. Yeah, okay, so we've got two more reactions for cross-coupling, and then I'll ask questions. It might take us up to the end of class, so timing might be perfect. Okay, so there's two more reactions that sort of involve palladium cross-coupling chemistry that are sort of worth mentioning. So we brought up sp2 couplings a moment ago and how sometimes sp2 couplings, you don't want to do it because of this beta hydride abstraction, but there are instances where that won't necessarily be a problem. And certainly one of the cases that you could imagine is an allyl bromide. Okay, and one of the reasons behind this is that you're not necessarily going to be stuck at that same issue of having a beta hydride abstraction because the beta hydride might not be able to align as well or various reasons. I've shown it as an allyl bromide. But it turns out that when you can actually stabilize that insertion, you can actually get even milder, what we call electrophiles. So you can imagine a situation like this. If you inserted into with palladium 0, just that sort of first step, right, you would have okay, so you have that palladium there, and again, your sort of beta hydride in this case might be there, and again, because that's perhaps not able to align in the appropriate reason for the appropriate way, it might not be able to sort of undergo this, although certainly you could imagine an allyne. But there's another reason why this won't beta hydride abstract, and the reason is that once you insert into a palladium species, especially with allyls, you get this sort of stabilization. So instead of say a beta hydride taking place, what can actually happen is, let's see if I can draw this in a way that might make sense. you can begin to sort of get the double bond here and push the electrons onto that side. So if I sort of label this blue, right, what's going to happen is you can actually get palladium. It's the same molecule, but you sort of flip-flop where the carbons are. Now that sort of palladium is out there. And so you sort of have this, what ends up being a resonance form, and oftentimes when you have this al complex, you draw it a little bit differently. So you'll see sort of al addition being drawn in a slightly different way, and the way that it's drawn is as a sort of a different ligand, where the electrons are sort of shared throughout that process. So again, it's a net minus ligand, but the fact is this is one of those situations where you're kind of like resonance, right? Kind of the same things that might make a proton more acidic, that you can sort of share electrons throughout a system. In the case of the al groups, that's certainly a similar thing that can take place. And because of this, what you'll often see is, instead of even having to use, say, al bromide, what you can actually do with palladium, or sorry, with al cross couplings, is you can actually use much milder situations, in particular palladium acetate. Okay, and so palladium acetate would be sort of involved in a sort of a Lilith cross coupling reaction. So if you take something like if you take something like al acetate and you want to do a cross coupling with this, you can begin to use this. But there's one other sort of factor that's involved here that I think is kind of important, and that's that this overall species, we've talked about sort of electrophiles as being carbon metal bonds, or sorry, excuse me, the electrophiles being carbon halogen bonds, and again, in this case we have this al species. But what you can begin to do is you can actually start to treat this through alternative processes. So you can actually do it with other nucleophiles. So once you're at a species where you have this palladium system here, so again, if we just do it with the palladium 0, what you can do is you can take, say, palladium 0 along with your acetate, and what you can do is you can begin to put in other nucleophiles. So I'm trying to think of an example that I know that I've seen in the past. So say, for example, if you had an acetate group here, see, I don't know that necessarily that would be that practical, but let's say you wanted to switch it out with, say, methanol or something like that. Let's see what the book has for examples. So the book actually uses carbon-based nucleophiles. So the book basically says that if you have a system like this, what you can do is you can take sort of anionic carbon sources, like the one that I've shown you here, and what can effectively happen is this will very readily displace the acetate, okay? And again, the mechanism in this process, I'll get to in a second, also involves this process. So what happens is the nucleophile will actually add in at the palladium source here, in much the same way that this reduction takes place here, right? So I mentioned earlier that if you take a base and you treat it with this, it will kick off. I'll sort of show the mechanism, but if you sort of look back at this, I could throw this up and have another board so we could relate back to it. I'll find a space right here, actually, so we can look at it too. So one of the things I mentioned over here, and I sort of said this, I've sort of shown it this way, but in fact, when you have that palladium hydride species, the base actually is cis in the leaving, and I'll try to make this make sense and why it's analogous here. If you treat this with, say, trialkylamine, what can actually happen is the base can assist in this process. So I've sort of drawn it as a reductive elimination, and then you just have the base in there to soak this up. But in fact, the base will accelerate this process. So, so again, you'll get the nitrogens, R3, H, Br, and palladium 0. And so it's often said that the base reduces the metal. I've often heard that said, and I was sort of remember being confused as a grad student because my professor was saying, oh, the triethylamine reduces the metal to palladium 0. And again, you can think about it as sequestering the HBr, but it does in fact help facilitate the breakdown of this process. In the same way, that's kind of what's going to happen here, is that if you end up with a system where you have this palladium-2, what can happen is when you treat it with a nucleophile, like this one here, what can often happen is a very similar transformation. Okay, so you basically are sort of adding almost like 1,4-ish. You're breaking the bond, you're getting this product and sort of regenerating the palladium-0. So again, this is something special about palladium. Again, it has to do two factors. One's the ability to stabilize this sort of high al system, and the other has to do with the fact that you have a species which can, for some reason, have the nucleophile added. And again, it's sort of analogous to this, but it also just has to do with the fact that the sort of electronics of the system are a little bit different than the others. But again, just sort of know the reaction for now, and that should be good. All right, and so there's one other reaction I'll let you guys go. The last reaction is a Sonic-Ashira coupling. Okay, the Sonic-Ashira coupling. Okay, so Sonic-Ashira coupling effectively involves the coupling of alkynes, and specifically terminal alkynes. So if you have a system where you have a terminal alkyne, and say, for example, you want to couple that to something else, we've seen in the past cases where we can do this, right? So ordinarily what we might do in a reaction like this in the past, right, is deprotonate the alkyne with like sodium amide or something like that, and then simply treat it with the alkyne. But again, we may run into some of the similar problems that we discussed earlier with the analogy of the Grignard. We might deal with side reactions, right? If you have the sodium amide in there, maybe you have other functional groups that are not compatible to the sodium amide. It's a very strong base. You might not necessarily want it. Alternatively, if you wanted to do that chemistry and attack an sp2 hybridized alkyl halide, you might not be able to as well, right? And so there are advantages to perhaps doing this in a way that doesn't necessarily involve acid-base electrophile chemistry. And what the Sonic-Ashira reaction does, I've always sort of wondered about this mechanism a little bit. It's kind of weird in the way that it works. But what you do in a Sonic-Ashira reaction is you use effectively copper in this process to catalyze this process, or sorry, as a way to get this reaction to go, as well as palladium. Now, there's some history behind this reaction. There was actually a reaction where if you have enough copper in this, you can actually begin to do this coupling without the palladium. Certainly palladium makes it a little bit easier, but the catalytic cycle behind this process needs some base as well. I'll explain that in a minute. Is that, again, if you start from the palladium 0, this is we'll start at the copper and we'll show you how to get it. I'm going to show a slightly different, I'm not going to show the catalytic cycle this way. It's a little bit difficult, but it's a little bit more complicated in terms of a lot of arrows going in different places. So it's well known, and it's actually, there's a reaction called click reaction, which is an azide alkyne cycloaddition, which uses palladium in a similar way as well. But it's well known that if you take alkynes, terminal alkynes, you treat it with copper and a little bit of base, what you can get to is alkynyl cuprates. So, and what you do in this process, you take this molecule and you treat it to sort of copper, in this case it's copper halide, okay, because it's copper 1. And what happens throughout this process is that the copper will actually coordinate. It's a little bit complicated, but the copper is going to coordinate to the alkyne. The base that's in there, say for example triethylamine, will actually deprotonate. And the overall process here is that you're sort of coordinating. That's going to that's going to make this a little bit more acidic by coordinating here, allowing for the deprotonation to take place. Then that negative charge is going to transfer onto the copper, which will kick off the X there. Okay, and so the sort of net result in this process is that you'll generate tributylamine hydrochloride. Okay, and without going into too much depth here, what's going to happen here is now you effectively have your metal, right? And previously we had alkyl tins, we had alkyl boronic acids, but now what we have is our cuprate ends up being the tin source. So if we think back to our previous insertion mechanisms, if you have this species, right, and you have a palladium-2 system that's already been inserted into the 2, right? This is based upon the mechanisms that we've seen previously, right? That sort of insertion into that bond. What will happen here is now you'll get that same transmetallation process. Okay? So if we just make this R2, oh, sorry. Right, so you've got this palladium species, you can go back to the other mechanisms. Then what's going to happen is you're going to do the reductive sort of oxidative insertion, the transmetallation. Then you'll generate your alkyl bond, you'll generate palladium-0. Okay? Now the byproduct of this is, if you just sort of look at the elements that are in here, what you're going to get to is sort of copper bromide again, right? Because you've got the copper and the bromide. So in fact, you can use copper catalytically, you can use the palladium catalytically, and you can effectively get this alkyne alkyl halide cross coupling to take place. Okay? Yeah. For the final exam, not for this next one. So for this next exam, because you guys got a short period of time, I would say know it for the final exam. Right now, just know all these reactions that I'm going to show you guys. And there will be questions for sure on the final exam that are going to solve these. Okay? Yes? Today's quiz? Or this week's quiz? Yeah, well, everything. But with emphasis on, everything up till last Thursday. With an emphasis, or Wednesday, whenever. With an emphasis on aromatic chemistry and amine chemistry. Yes. What's that? Like previously, we'll have time tomorrow, next class, because we just have metathesis to cover. So I can probably get through metathesis in 20 minutes. So the final hour next week will be our sort of review. Okay?